All right, in this video, we're going to introduce the concept of momentum. And seemingly momentum is very different than anything we've talked about so far in first year physics. And so let's start by trying to think of what momentum means. And momentum is a word that is very, very commonly used in our everyday lives when we're not talking about physics. And in that context, I think it means to have some sort of momentum. It's hard to use not the word momentum. It's so common, but to have some movement in a certain direction. Oftentimes we'll use it to refer to something in the context of business or some project getting done. So some sort of like positive development, but I do see that the idea of motion involved. And so when we think of momentum more in a physics sense, and especially if you've seen the concept in your high school years, we think of momentum as more of a quantification of mass and velocity, how massive something is and how fast it's moving. We're going to find that to be a simplistic definition, but let's write it down for now. Momentum is a combination of some sort of motion, and I think it's safe to say that the faster something is, the more momentum it has. So let's write that as speed, and something to do with size or mass. And so if we're talking about something in our everyday lives, we might talk about something that's very, very massive and has some motion. If we're talking about a more physical definition, we're specifically talking about mass times velocity. And so we'll introduce this as our first sort of definition, but very quickly we're going to realize it's not good enough. So we're going to use the letter P for momentum. And momentum is a vector, and so we'll put the vector sign on top of it. And the first definition we'll give it is its common understanding of just mass times velocity. And I look at this equation here, and P equals m times v. Well, m is a scalar, we all know that. V, velocity, is a vector, and p is a vector, and so p should go in the same direction as velocity. But it's a bit of a weird thing. It's like, why did I just multiply mass times velocity? What does that mean? It's kind of ridiculous. It has a unit of kilograms meters per second, and I look at that unit, and even more so I think, that's a little ridiculous. What is the meaning of mass times velocity? Why do I multiply a mass by a velocity? What sort of important physical quantity does that define? I mean, up until this point, we've talked about velocity and acceleration and forces, and they had a fundamental meaning. It was a combination of other things like mass and position and time. We put them together to get these new quantities like velocity, like acceleration, like force. But I'm a little stumped when it comes to this mass times velocity. It seems kind of thrown together. What is the fundamental meaning of mass times velocity? What if I take two other of our fundamental quantities and put them together? What about time and mass? What's time divided by mass? Is that something? You should call it something. It doesn't have a meaning. It doesn't have a physical meaning. So there has to be something more to mass times velocity that makes it a quantity that we care about. And so that's the real question here. Why do I care about momentum? Why do I care about mass times velocity? Let's find out. So what we're going to try to do is to derive a more fundamental definition or understanding of momentum. So let's say fundamental definition, and hopefully that leads to a more fundamental understanding of momentum. Okay, so what can I do? Well, let's take the derivative of momentum. You might be saying, why? Because I think we're going to get something interesting. So we can take the derivative of any quantity, and so let's choose to take the derivative of the momentum. With respect to what, you ask? Time. How does momentum change with respect to time? Well, if we're saying that momentum is equal to mass times velocity, then we are taking the derivative of mass times velocity with respect to time. And that's something we understand a little bit better. Now, to actually solve an equation that's taking the derivative of two terms, mass and velocity, we have to use something called the product rule. And the product rule is something that you would learn in your first year calculus or math courses. And so what we do is we take the derivative of the first term and multiply by the second term, plus the derivative of the second term multiplied by the first term. And so we see this as dm by dt. So I'm just taking this bit right here, multiplying it by the velocity. And then I'm going to add the first term, m, and multiply that by the derivative of the second term, that is dv by dt. Okay, so that's just a standard product rule. Maybe we'll make a little note of that in case you're less familiar with it. You can go look that up. But the product rule allows us to do a derivative of two terms, or of a product of two terms. Okay, and so what is this going to be equal to? Well, let's look at each of the terms specifically. The first one is dm by dt. That is the derivative of mass with respect to time. So I ask you this: how does mass change with respect to time? dm by dt is quantifying the change of momentum with respect to time. What is dm by dt? Well, up until this point, and I think it's safe to say, let's continue this trend, that mass has been a constant. We haven't had a changing mass in any of our problems. And so if mass is a constant, and I'm taking the derivative of a constant, what do I get? Always 0. And so we'll get 0. So that term gives us 0, since m is constant. And we'll multiply that by v, of course, that whole term goes to 0. And finally, we're left with mass times dv by dt. Now, that's a derivative that you're very, very familiar with. In fact, that is the fundamental definition of what? Acceleration. And so dv by dt just becomes a. That term cancels out. And we are left with the derivative of momentum is actually equal to mass times acceleration. Mass times acceleration, mass times acceleration. That seems very, 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 very familiar to me. Of course, that is just the net force. By Newton's second law, the net force on an object is equal to its mass times acceleration. And so what we have shown is that dp by dt is equal to, call it F net, call it the sum of the forces. It's not a specific force, it's all the forces added up together. Wow, okay, so what are we talking about now? We are talking about a new, more fundamental definition of the force and the momentum, the relationship between the two. The reason why we are looking at the momentum seems to be somehow related to the force. basically the derivative of this new term momentum is equal to net force. Okay, let's put that in a box. That's interesting mathematically, but what does it mean physically? Why is the study of momentum something that is important? Well, let's consider the situation where the net force on an object is equal to 0. Now, that doesn't mean that we are talking about an object that has no forces on it. We've seen many, many examples of objects in equilibrium where we could have 2 forces, 4 forces on an object, and they all balance one another to give us a net force of 0. That is 0 acceleration, equilibrium. And so let's think about what happens in those circumstances. So consider what happens when we set an F net equal to 0. All right, well, we said that F net now is equal to dP by dt. If that is equal to 0, what is P equal to? If the derivative of P is equal to 0, what must P be equal to? A constant, any constant, right? Doesn't matter if it was the number 3, a letter, whatever. If it doesn't change and you take its derivative, you get 0. So what we are showing is that P is any constant. Or more fundamentally, that P is a constant. That's the key to the entire thing here. That's what makes momentum such an important part of our learning, is that we have a constant when it comes to situations that have a net force of 0. Right now we're just talking about a single object. I'm saying if I have a single object and I have no net force on the object, then that object's momentum must be constant. Its mass times velocity must be constant. When we think about that, mass is always constant. Velocity is therefore constant if I have no net force. I already knew that. What's the big deal? The big deal happens when we start talking about multiple objects. Multiple objects that interact with each other or collide with each other, and we look at their total momentum before and after the collision. If the net force on those objects is equal to 0, then we will have a constant momentum. The only reason we study momentum, the real reason we study momentum, is because it's a conserved quantity in certain situations, in lots of situations. And that conservation of momentum allows us to figure out other important factors of our problem. And so we're going to not care about momentum for momentum's sake. We care about momentum because it is a constant value and it allows us to figure other things out. Let's write some of that stuff down. All right, so we have shown if there is a net force of 0, on an object, and as we will see, or a set of objects. And that's where momentum gets particularly interesting. That momentum is conserved. All right. And so now we have an understanding of this quantity as well as an appreciation of why we're even doing momentum. It's because of the conservation nature of momentum that makes it important. Incidentally, you could actually rearrange that equation in terms of P. It's something that is more appropriate for upper year courses, but I'll just show it to you very quickly. You're not responsible for this, but we can rearrange this by putting the dt on the other side. And we're left with this equation here. And what you can do to both sides of them is you can integrate those equations. You can integrate this equation, you can integrate that equation. The right-hand side just becomes P, and you have an equation of force on the left side. And so P is actually equal to the integral of the force with respect to T. That's another way of looking at it, but that's a bit too advanced for first semester of first year physics. And so now I'd like to look a little more closely at momentum for a set of objects, and specifically two or more objects. As we've seen, conservation of momentum for a single object is not that interesting, because if mass doesn't change, then either does velocity. And so nothing changes, big deal. But in an interaction between two objects, and specifically I'm talking about collisions between two or more objects, we can have an exchange of momentum where some momentum from one object is transferred to another object, yet there is an overall conservation of the momentum before the collision and after the collision. And again, that can tell us a lot of interesting science. So let's introduce the concept of collisions. And collisions is really the most important functional part of momentum. And so what we are going to define a collision as, let's define this collision as, when two or more objects approach one another interact with each other. And what do we mean by interact? It can be something like, hitting another object, but it doesn't actually have to be. Essentially, funny enough, the interaction that we're talking about is an exchange of momentum. And so when we say they interact, you can, in some ways, define this interaction as an exchange of momentum. And then they will move away from one another. But they don't actually need to. You can have collisions where two objects interact and then stick together. So let's see. Or stick together. And there's even, doesn't sound like a collision, but there's certainly variations on this type of problems where two objects actually start together and then they'll separate. Two or more, in fact, will start as a single object and then they'll explode as opposed to collide into various objects. But they're treated exactly the same way. And so we'll say two or more objects approach one another, interact by exchanging momentum, and move away from one another, or stick together, or start together. Okay, cool. Really, this start together part should be up here, right? Where they're either approaching one another or they start together, but we'll just leave it there. Okay, and so let's talk about different types of interactions. And so when we first describe this interactions, we were talking about collisions. And when we think of collisions, where you think of directly things hitting each other, colliding together, a body check in hockey, or a car crash, or playing pool, or table tennis, or something like that. And so these are directly interacting. Let's kind of classify these as directly interacting. And feel free to think of examples yourself. They're, things hitting each other, colliding with one another. And some examples include a car crash, or playing pool, also known as snooker, which I will write there. It's a specific game like pool. And then there's also interaction at a distance. You don't have to necessarily even touch one another by our traditional definition. You can interact without And you can think of examples like that. I'll give you a second to think of a collision where two objects don't even touch one another. I think some people are saying magnets. Yes, absolutely. Magnets are a very good example. If I have two like magnets, let's say where their sides facing one another are both positive and they are forced together, they can kind of come like this and move apart from one another because there's a repulsive force between them. They never do touch. You could see the same thing with atomic and nuclear particles. If we have two positive charges moving towards one another, they will repel one another. So atomic, particle, charges, etc. And even the same thing happens with gravity, though it's far less obvious. When we think of gravity, we usually think of direct interactions. In fact, you could think of plenty of examples of directly interacting gravitational collisions, for example, an asteroid hitting a planet. But in fact, there are ways to interact gravitationally with another object without ever touching it. In fact, we do this maneuver quite a lot in what's called the slingshot effect. And so if NASA or any other space agency is sending a spacecraft to another world, let's say to Jupiter or Saturn or something like that, oftentimes what they do is they slingshot it around nearby planets, perhaps Mars or Venus, etc., so that it gains momentum. It can actually do a sort of flyby and steal some momentum from the planet, increasing its own speed. And so that's a very cool example of an interaction at a distance. All right, so now comes our look at how we actually handle problems that have a collision between two objects. Let's look at that carefully. So how do you handle a collision between two objects? All right, so let's create such a collision. Let's say we have ourselves one mass here, and we're going to have ourselves another mass here, M1 and M2. M1 and M2 have an initial velocity when this problem starts sort of in this direction. meaning they are headed towards one another. And they're going to go towards another, they're going to interact, and they'll move away in a very traditional way. And so let's pretend that we have an interaction like that. Now, did they hit each other? Were they repelled by each other because they were opposite charges? I don't know. It doesn't really matter. Let's analyze this mathematically by saying that the sum of momentum of both of our objects before the collision is going to be equal to the sum of the momentums after the collision. So this is us stating our conservation of momentum. We've shown that conservation of momentum is real, so now we're saying we're going to use it. We don't see any net force on these objects other than the interaction of each other, which is not going to exclude us from using the idea of conservation of momentum. So let's split up this formula here into its two parts. And so when I say the sum of momentums, I mean the momentum of this mass and that mass before the collision. And so I'm going to write each of those momentums as P1 initial plus P2 initial. So this is M1's momentum, this is M2's momentum. And that is going to be equal to both of them afterwards. They're going to end up colliding, moving away from each other. There may be a transfer of momentum from one to another, but the total momentum will still be the same thing. P1 final plus P2 final. This P is too small. There we go. All right. And we also have a formula for the momentum that we can use at this time as well. It's unlikely we know the momentum of these objects, but we're far, far more likely to know and want to know the mass and the velocity. And so P1 initial should be M1 V1 initial plus M2 V2 initial plus M1 V1 final plus M2 V2 final. All right, there we go. So that gives us a useful formula, but what we're going to very quickly realize is that if this collision is occurring in 2 dimensions, then we're going to have to be very, very careful about vectors. Now, if it happens in 1 dimension, it's super, super easy, like very easy, easier than 1-dimensional kinematics, really. I'm not just exaggerating here. Because if I have this formula and objects are just moving in a straight line, let's say they're both going this way and they bump into each other, or even if they're coming and they hit head on to one another, this equation is very, very easy to use. If you, let's say, just had a single unknown, you could easily rearrange the equation and solve for that unknown without too much trouble at all. Things get a little more difficult when we start thinking about 2 dimensions, like this collision here. Did not mean to use my eraser there. Like this collision here. Because in this collision here, this collision is occurring in 2 dimensions as opposed to 1. And so we have to be a little bit careful about how we apply our momentums in each direction, because we can't use momentum this way and momentum this way and simply add them up with one another. Because as we know, momentum is a vector and it's made up of mass times velocity, and velocity is a vector. When you have 2 vectors going in different directions, it's not as simple as just adding 2 numbers up. And so what we'll do is we'll deal with collisions in 2 dimensions by applying our conservation of momentum equations in each direction separately. Now we're totally used to doing this because we have done it numerous times for different types of vectors. And so why should momentum be any different? It's a vector, and so momentum is conserved. Yes, true. But when we're actually using it, we're going to use the fact that it is conserved in each direction separately. And so we can write that not only is the initial momentum equal to the final momentum, our useful form of that formula in 2 dimensions is its x and its y version. That is, the sum of the total momentum in the x is equal to the sum of the total momentum in the x again, but after the collision. So P initial x equals P fx. Same thing happens for the y or any other direction. Okay, and so now we realize that if we have to apply this formula to this sort of equation, we're not going to just have one equation, we're going to have two. We're going to have one of those in the x and one of those in the y direction. And putting them all together will give us our means of solving our unknowns. And you have to be ready to do components, etc. And so now, before we jump into actually using our momentum equations, let's define a few types of collisions. Now, we've mentioned different types of collisions already, but let's give them some names. And so these are the types of collisions that you will encounter. The first one is a pretty ordinary type of collision where we have objects coming together and then recoiling away after the collision. And we're specifically going to talk about a particular example of that recoil. So you could say two coming together, interacting, and moving away from one another. Let's define what is known as the perfectly elastic collision. So in this, we not only have objects coming together, and then recoiling after a collision, it must happen with no loss of energy. Also known as conservation of energy. Now, we haven't defined energy yet. Energy is still to come after momentum. It's the next major topic that we learn. But I'm going to ask you to remember perfectly elastic collisions and remember momentum when we get into talking more about energy. Those problems will come up again, and there will be problems where you can use conservation of energy and conservation of momentum simultaneously. But for now, we'll probably stick with other types of collisions. But just quickly, can anyone give me a few examples of perfectly elastic collisions? Where do you see things coming together, interacting, moving apart, with little or no loss of energy? Very, very little types of energy. I think we talked about magnets before. That's a good example, especially if you have, let's say, magnets on a frictionless surface, right? Like an air hockey table. You take two magnets, discs or whatever, you bring them together. perhaps they will repel one another and they'll move apart again. There's no loss of energy there. Similarly, we see this with particles collisions. Other examples that people can give I've heard Newton's cradle. That's an interesting one. So Newton's cradle is like 4 of those steel balls suspended from 2 wires, and you kind of like pull one back and it comes and hits another one, and then the last one will off, comes back. And what's happening is momentum is being transferred through that series of balls. Now you're saying to yourself, but you can hear some sound. Isn't sound a type of energy? Absolutely, but it is a minimal loss of energy, and we can add it to here. There's a couple of sports that use perfectly elastic collisions, certainly in pool or snookers or billiards, whatever you want to call it, even though we hear that when the balls hit one another, they're very, very close to conserving energy, and they do conserve momentum as well. And the last example, which I really, really like, is curling. Not that I'm much of a curler. I think I've only done it one time, but it is a sport with very, very fascinating physics. Watch it sometimes and think about the conservation of momentum from one stone to the next, but the physics of actually throwing the stone down the length of ice and the sweeping involved in the melting of snow right in front, where, you know, when they sweep right in front of the, see, a lot of people don't know this example. Curling is a pretty obscure sport, but what the brushers do, the sweepers do, is they're actually melting the ice right in front of the curling stone, and that changes the friction between the stone and the ice, causing different outcomes. So anyway, if you don't know what curling is, or I would recommend everyone go ahead, Google or YouTube some curling and watch the physics of it. It's quite fascinating. But moving on to other types of collisions, let's talk about perfectly inelastic collisions. So in a perfectly inelastic collision, we have 2 objects starting apart, moving, coming together, interacting, and staying stuck together. So objects here will stick to one another after the collision. And this type of collision, energy is definitely not conserved. And so we will do plenty of these types of examples in this chapter, because you do not have to worry about energy at all. So basically what we're saying is energy is not conserved between the collision itself. It's lost, it's transferred, let's say, to another form. And finally, we also mentioned the idea of explosions. And so explosions do count as collisions for our purposes. And in an explosion, we basically have a separation of an object into parts. So separation of an object into parts. And just a couple of examples of each of those perfectly inelastic collision and explosions. You can again think of these in your own lives or from science experiments that you know. A good one for perfectly inelastic, one I like, is again a collision in space. Most often collisions in space, whether comets hitting Jupiter or two asteroids colliding, oftentimes they will stay together afterwards. And so that is an example where we have a perfectly inelastic collision. So let's write example, let's say comet hitting and landing, if you will, so it would be pulverized on a planet. And the explosion, a good example of that, other than, an explosion like a bomb or something like that, a more interesting scientific one is a decaying atom. Okay, and so now we're going to use our knowledge of these collisions as well as how to use our conservation of momentum equation, both in one-dimensional and two-dimension, to solve problems of all of these different types. So one last thing that we have to do in momentum is to talk about the concept of impulse. And so what is impulse? Basically, impulse is a measurement of momentum that an object can gain or lose. Now you might be saying to yourself, well, what about conservation of momentum? Doesn't conservation of momentum mean that the momentum doesn't change? Well, no, we're going to have some kind of interaction with our object. So take this ball, for example. This ball is bouncing, and every time it hits my racket, its momentum is changing. So sometimes it goes quite high, and sometimes a little bit not so high. And so each time the momentum is changing by a different amount, because essentially the momentum is being transferred. Sometimes the momentum is being transferred from the ball to the racket, and sometimes the racket transfers some momentum from the ball, from the racket to the ball. And in those cases, the ball will go higher, it will go faster. And so this doesn't have to do with conservation of momentum, because with conservation of momentum, we talked about the momentum conserved between two objects. But now what we're going to look at is how the momentum changes for a single object in some kind of a event. It doesn't have to be a collision. It can be something like a ball bouncing off the ground. Basically, momentum is either gained or lost by our object. And we're going to define that as impulse. And so let us define impulse here. As I said, this is momentum that a single object acquires or loses changing its original momentum. And non-intuitively, impulse is given by the capital letter J. J for impulse. It was being used for other things more important than impulses. And the SI units for impulse, we're going to define as nanoseconds. Sometimes we can also write it, since it has the same units as momentum, you could easily see that as kilograms, meters per second, but this is the equivalent to that term. And this is the standard way of defining it. And so let's see what happens when we take an object with some existing momentum and we apply an impulse to it, negative or positive impulse to change its overall momentum. So if we apply an impulse to an object, then we're going to end up with a final momentum that is equal to whatever my object's initial momentum was plus j. That's pretty obvious, right? What we just have is PF, momentum final equals momentum initial plus my impulse j. And so we can rearrange that for j and see that j is just therefore equal to the change in momentum, PF minus P initial, or we could write that as delta P. All right. And so that is how we're going to define our momentum. And the impulse itself, we can look at it carefully and see how we might apply an additional momentum, or how we can take away a momentum. So basically what I'm asking for is how do you get an impulse? Let's check. So again, with the ball and the racket. Now, if I just drop the ball onto the racket, notice it doesn't come up as high as where I dropped it from. Not nearly so. Even if I held this completely straight, basically the momentum going in, that is the velocity it has right before multiplied by its mass, mv, is going to be greater initial than it is final. Once again, if it had the same velocity, it would come up to the same height. And it doesn't, not nearly. On the other hand, we can actually go a lot bigger. We can move our momentum, we can move our racket upwards and end up going much higher. So I'll drop it from here, but it ended up going much, much higher. And so what happened is that I gave it more momentum, that by really applying a force from the racket to my ball, I was able to increase its momentum. I gave it some impulse. And so the question was, how did that happen? What was the event like? Well, if we were to look at sort of a slow motion replay, what you would actually see is the ball would hit and be kind of crushed. It'd be like squished up against the racket. The racket itself would bend as well. And because it was moving upwards, it would transfer some of its momentum to the ball. That doesn't happen instantaneously. It takes some time. Basically, it's force applied over some time interval to increase momentum. So again, I'm going to give it a force, this pushing force, and I'm going to apply that force for an amount of time. And that combination, the more force I give it and the longer I give it that force, I'm going to end up with an object that has a higher and higher momentum. So once again, now I'll just give it a little force for a little amount of time, and it ended up going a bit higher. If I increase that force this time, let's see what happens. And we ended up with a greater momentum. Okay, super. So what I'm basically learning is, yes, J is the measurement that defines the change in momentum, but it actually seems to be possible for us to calculate that value by using force. If we apply a constant force to an object, we would have a value of J equals the force applied multiplied by time. So that's it. So J would be equal to F times T. then that would actually be a pretty strange force to apply. As you could probably tell, when I was moving my racket and hitting the ball, it wasn't a constant force that was being applied to the ball. When the ball first hits the racket, you have less force being applied to it. But as the ball kind of squishes against the racket, more of the surface area is touching the racket, and the force on the ball is increasing until the point where it starts to leave the racket. And as it's kind of bouncing back, then its force is decreasing. You can actually model that in different ways with functions that are more complicated than j equals f times t. That's not a very realistic formulation. A more realistic, not terribly more, but certainly more realistic force being applied would be one that's being applied unevenly. And so maybe a force that is a bit more realistic would look something like this. Let's put force there, time here. This is our 0 mark. And as, let's say, the ball is bouncing on the racket, its force will increase up to a point and then decrease linearly as well. And so, well, it's supposed to look a little more even. Let's say like that. That's pretty good. Okay, cool. And so there's actually a lot of different formulas that you can use for impulse. And so if you are doing an impulse question, do look carefully if they're talking about a force being applied, how the force is being applied. You may encounter something along the lines of j equals 1/2 times the force times t, and other various types of equations as well.